Hi everyone, welcome back to the Rack course. Uh, In previous sessions, we discussed about the text embeddings with different techniques like a cosine similarity and Euclidean distance, and then we discussed PCA, dimensionality reduction, and large data and all. So today we are going to discuss about the clip is like a generating embeddings for images and text using clip. So clip is nothing but a context to language image and pre-training. Is a multimodal that learns that relationship between images and text descriptions. It converts both image and text into embeddings in the same vector space. You can see the image in the flow diagram, images creating embeddings using clip and then image and vector database and find the relevant content from the image and creating embeddings user query and the multimodal is generating the response. So now the problem, you you want to classify image or perform cross model matching between images and text using embeddings. So use the solution as I mentioned, use contracts to language image pre-training to generate embeddings for both images and text, enabling cross-model matching and classifying. Multimodal retrieval with the clip, generating embeddings for all images and text that you want to add to the vector store. Both images and text are converted into numerical embedding vectors using a model such as clip, which maps different modality into a shared embedding space. This allows the system to compare images and text using the same similarity metrics. So the query processing, how it will be is like when a user asks a question, use clip to generate a embedding for the query. The example query you can see, how do I reset my password? The query is converted into the vector representation that captures its semantic meaning. The similarity search, compare the newly generated query embedding with the embedding vector store in the vector store. The system calculates the similarity between vectors using a metrics such as cosine similarity. The most similar vector represent content that is semantically related to the user query. So retrieve relevant content. The vector store returns the top k most similar result, which may include. I discussed already these things in previous videos. Now the relevant image and related to the text chunk diagrams or visual documentations. So these retrieval items from the context for answering the user question. So multimodal reasoning, how it will use. So finally, send a retrieved image and a text to the multimodal that can interpret both the modality simultaneously. The multimodal module model analyze the combined information and it generate the final answer for the user request. So this is a practical example how to calculate multimodal embedding using a clip. So Torch is the PyTorch library used for deep learning model and Pill is like a user to open and process the image files and it transformers here clip processor and clip model is a Hugging Face classes for loading the clip model and processing the inputs. So load the pre-trained clip model here, clip model data from pre-trained and giving the model name. So clip can understand relationship between image and text we discussed. So load the processor associated with the model. Processor equals to clip processor dot from pre-trained and the processor prepare both text and images into the correct format required by the model. So define text description that we want to compare with the image. So the description is like a if I give like a photo of dog or cat, a photo of a cat, a photo of a dog. So these are the text chunks. Load the image from the dataset directory and pill is used to open image file. So now we are disabling gradient computation. So this improves performance because we are only performing inference, not training. So that's why glad. Then we are giving the process both text and image together. The processor converts them into the tensors that clip model can understand in the tensors. So you can say text description, image input, and written PyTorch tensors and pad sequence to the same length and a truncate if input exceeded model limits. So, and next one is a pass the processed input to the clip model. The model compute embeddings and similarity score. So, output is equal to models like inputs we are giving. Extracting similarity score between the text and image. Logits per text contains the similarity between each text description and each image. So convert similarity scores into the probability. Softmax normalize the value so that they sum to 1. This tells us to probability that a text description matches a given image. So you can see the flow here, the output, it will come like this. Now we are printing the probabilities. So print all full probability matrix and this shows how likely each text description matches the each image. Print the probability that first image corresponded to the first description and the probability this is means and the row first one is like a row and a column and dot items and printing that probability next. The first one is 0.9 and second one is 0.8. Now connecting images and text in a shared embedding space clip. So clip contracts to language image pre-training in a multimodal model trained on millions of images, text pairs collected from the internet. So the model learns to map both image and text into the shared vector space where semantically similar content appears close together. The key idea is that content with the same meaning should produce similar vectors, regardless of whether the input is an image or text. For example, image a photo of dog or text a photo of dog. So both input produce embedding vectors located close to each other in vector space because clip learn this association during training. What is zero shot classification with the clip? Clip enables zero shot image classification, meaning it can classify images without a task specific training. Instead of training a classifier, you simply provide candidate text description and clip ranks them by similarity to the image. Example, a photo of dog, a photo of cat, photo of car. So clip compute similarity between the image embedding and each text embedding, then select the most similar label. Um, Here you can see the formula. This makes clip extremely flexible because adding new category only requires writing new text prompts, not retraining the model. When clip is useful, clip is especially useful. Many possible categories suggest one is a traditional classifier requires retraining when categories change. Clip allows new categories to be added simply by writing new text descriptions. So product classification system, a red running shoe, a leather office shoe and a hike shoe. So label training data is limited because clip is already pre-trained on large data set. It works well in low data environments. This is useful when labeled training data is scarce, expensive, difficult to collect. Now, the next one is a cross-model retrieval. Clip works well when images and text are closely related, enabling retrieval across modality. So, example domain is a product catalog, scientific papers, and technical documentation media such systems. Example query, you can see here diagram of a neural network. The system can retrieve relevant figure, diagrams, related images. So clip in retrieval system. Clip enables across multimodal search where text queries retrieve images, image queries retrieve text description. The workflow you can see generate embeddings for image and text, store embeddings in a vector database, convert the user query into embeddings, and retrieve nearest vectors using cosine similarity. This allows the system to find visually relevant content from textual queries. A simpler approach for most RAG systems. For many RAG applications, a simpler architecture works better. Instead of storing image embeddings directly, the system use a multimodal LLM to generate text description of images, convert those descriptions into text embedding, stores the text embeddings in the vector database, retrieve relevant description during search, and send the original image to the LLM only when needed. So UI screenshot, you can see login page showing the reset password button, and chart is like a bar chart showing quarterly sales growth. These are like a general description. Why this approach is often better? Text embedding models are highly optimized for semantic search, which makes them very effective for retrieval. Advantages like simpler pipeline, better semantic matching, lower system complexity, easier debugging. So clip direct image text mapping can introduce additional complexity that is unnecessarily for many RAG systems. So clip is powerful for multimodal understanding and cross-model retrieval, but it is not always required for RAG. Two common approaches like a clip-based retrieval, embedded images and text directly retrieve across modality. So text description approach is like a converting images to text description. Use a standard text embeddings and retrieve description and pass images to the LLM only when needed. So for many RAG systems, the text description pipeline is simpler, more scalable, and easier to maintain, improving such result with the hybrid search approach. So this is another one. So you want to improve retrieval quality by combining multiple search technique instead of relying on a single one. So there is a solution that is a combined BM25 based keyword search with vector similarity search, then match their ranking using reciprocal rank fusion. A keyword search ranks a document based on exact term matching using BM25. So a embedding model generates an embedding for user query. A semantic search rank documents based on the vector similarity. The ranking for both searches and merge into a single ranking. So you can see the flow sorted by relevance is like a chunks and then keyword vector database, and now it is going to the keyword search BM25 algorithm, and then and then it goes to tell me something interesting about the disease in their history in the user request, and searching creating embeddings and performing the similarity. So both is searching in the knowledge base, so then it is providing the response. So this is the one flow. To implement hybrid search, you need three components. First, it's a BM25 for keyword based ranking, and which is especially useful for product name, ID, code, or and domain specific items. So a text embedding model for semantic similarity, a rank fusion method to match both ranking into a single result list. So how to optimize similarity search by combining similarity search and keyword search. So import the BM25 ranking algorithm. BM25 is a popular keyword based retrieval algorithm used in search engine. From rank BM25, import BM25 or KAPA, import pandas to help with the ranking and organizing result. So import pandas as PD, define a list of text chunks documents. Each item represents a small document into the dataset. As you can see the chunks, text chunks. So tokenize each document. Tokenization means splitting text into the individual words, and BM25 requires a tokenized input, and initialize the BM25 model using tokenized document. The model calculate term frequency and prepare the ranking structure, and define the user query, tokenize the user query in the same way as the document. Tokenized query equals to user query dot split, and a compute BM25 relevance score, and each document receives a score based on how well it matches the query keyword. Rank the document based on their BM25 scores. The step one is convert scores into a data frame. Short scores in descending order, highest relevance first, and extract the document index position. That is like a ranking keyword search, and giving this create a table of score and a short highest score first, and get the document index converted to the list. So printing ranking result, you can say 0, 1, 2. Now this is like a different approach. Import sentence transformer commonly used for embeddings. So create a data frame to store text chunks, and each row represents one document. Initialize the OpenAI client. The API client is retrieved the environment variable OpenAPI key. So then create an empty list optional helper list for embedding. Define a function that generate embeddings for a given text chunk. So call the OpenAI embeddings API. The model converts the text into a numerical vector representation. So it you can see that giving like embeddings and embeddings, text embeddings 3 model, and the text input we are providing, and access the first result, extract the embedding vector, and return the generated embeddings. So generated embeddings for each document, and the apply function runs create embedding on every row. So generate an embeddings for the user question, and these embeddings will be compared with a document embedding. So then we are doing that compute cosine similarity between document embedding and then query embedding. Cosim measures how similar the meaning of the vector. So you can see that embedding, document embedding and query embedding we are providing in the data frame, and rank document based on similarity score. Highest similarity equals to most semantically relevant document. So semantic ranking, semantic search, and then print displaying the ranking result, you can see. So create an empty list to store combined RRF scores, like combined score, loop through each ranked position, and K is the constant user reciprocal rank fusion, and it reduces the impact of lower ranked result. Compute RRF score and formalize like a RRF equals to 1 by K plus rank keyword plus 1 by K plus rank semantics. So ranking keyword search is rank from BM25 keyword search, and a rank semantic search is like a rank from semantic embedding search, and store the calculator score. Combined score is dot append, and convert the combined score into a diagram, and sort the document by the combined RRF score. Higher score equal to better ranking, then display the final hybrid ranking. So we can discuss in depth of hybrid search in rank system. So hybrid search is combines the two independent ranking signals that capture different aspects of relevance. One is a similarity. Vector similarity search is a measures the semantic closeness in embedding space, and keyword search is a lexical search. So matches exact term in a document. So these two signals are combined using reciprocal rank fusion, which measures ranking by giving higher score to documents that appear near the top of multiple result list. Why hybrid search works? Hybrid search works well because a keyword signal and semantic signal are complementary, and keyword matching is like a keyword search focus on exact word matching. It is highly effective when query contains a precise identifiers such as product ID, legal litigations, and a medical code or a technical identifier, something like this. So only document contains the exact identifier. You can see the example SKU 4792. This is like a exact identifier we should match. So semantic search done. Semantic search uses embeddings to understand the meaning of text. It performs well when users express the same idea using different words. For example, how can I change my password? Steps to reset your account credentials. This is like a document. We can extract it even through the wording. A different embedding identify the similarity. Semantic similarity. Reciprocal rank fusion is a RRF, is a hybrid such combines keyword ranking and vector ranking using reciprocal rank fusion is a scoring. So here we are main components like a document, and the rank of document is the ranking list and a constant. So the document that rank a high is multiple ranking lists receives a higher scores. This method ensures that documents important in both the keyword and semantic search are prioritized. When to use hybrid search? Hybrid search is particularly useful when the corpus contains identifiers or specialized terminology that embeddings cannot reliable captures. Example is like a product catalog queries containing product SKUs, and then SKU 4792 is the system must reduce the exact product entry. So for example, legal documents, so article 230 or section 230 something, even through the number or similar, they may refer to the different legal concept. So another example is like a medical system. Healthcare documents often references diagnosis code. So this is like these identifiers must match exactly, making keywords such essential. Technical documents like engineering documents often includes API endpoint or database identifiers. Embedding models may not reliably capture these character level identifiers. Uh, why hybrid search improves RAG retrieval? Hybrid search improves retrieval quality because keyword search captures exact term matches, and semantic search captures the meaning, not intent, and combining both improves precision and recall. This approach helps ensure that both exact identifiers and conceptual relevance, fluence, and the ranking. What key takeaways from this explanation? Hybrid search combines the strength of keyword search and semantic search. It is especially useful when working with a data set containing product SKU, legal citations, medical diagnosis code, and API names, database identifiers. By matching both signals using reciprocal rank fusion, hybrid search provides more reliable retrieval for RAG system. When to use hybrid search in RAG system? Hybrid search is useful when user queries command natural language with precise technical terms. We have discussed multiple examples. How do I configure SSL for endpoint? So the query contains two types: natural language intent configure SSL and exact technical identifier like a API v to users. So semantic search helps interpret the intent, while keyword search ensures the exact endpoint path is matched correctly. So hybrid search combines both signal to produce better retrieval result. When not to use hybrid search is unnecessary for pure knowledge retrieval where user pays questions naturally without technical identifier. Example, how do I reset my password? In this case, semantic search alone is sufficient because the system only needs to understand the meaning of the question. So adding a keyword search, so such as BM25, increases complexity without improving retrieval quality. Start with semantic search first. A good development strategy is like start with semantic search, evaluate retrieval performance, and add hybrid search only if needed. Hybrid search should be introduced when you observe exact identifier mismatches, product codes not being retrieved, API endpoint missing from result, user feedback indicating failed search. So this information can be discovered through retrieval logs or such analysis. Computational cost of hybrid search. So hybrid search increases the system complexity because it requires running two separate retrieval systems. Typical pipeline is like a vector search retrieves semantically similar documents. Keyword search BM25 is retrieve documents with exact term match. Rank fusion is match both results list. So this means two retrieval operations, additional ranking computation and more infrastructure to maintain. Trade off for like a recall versus complexity. Hybrid search improves the recall for queries containing identifier or specialized terminologies. However, this comes at the cost of increased complexity. Challenge include like a maintaining two retrieval pipeline, tuning the rank fusion parameter, handling cases where ranker disagree. So reciprocal rank fusion parameter, that is okay. Hybrid search typically uses RRF to combine ranking. So as we discussed already this, now effective of parameter k. The parameter k control how much importance is giving to ranking position. So 10 to 20 is strongly favored documents that rank very high in the both retrieval. 60 to 100 is gives more weight to lower ranked result. So common default is k is equal to 60. This value balance contribution from both ranking systems. And the best practice is like use hybrid search when queries include identifiers, document content, technical terms, and exact match are important. Avoid hybrid search when queries are natural language questions and semantic search already provided good retrieval quality. Start simple with the semantic search, then introduce hybrid retrieval only when necessary. What are the key takeaway from this explanation? Hybrid search improves the retrieval when uh, when queries combine semantic and exact identifier. However, it introduces higher computational cost, more complex infrastructure, and additional tuning requirement. So, for most RAG systems, start with semantic search, monitor search performance, and add hybrid search only when identifier based queries require it. So this is about like a hybrid search. In next video we can discuss performing text classification using embeddings with all these techniques. So keep following my videos. You can get like a more important information. Please subscribe my channel. Thank you. Have a nice day.